Alrighty, welcome back to another exciting foray into the world of mathematics. Alright, anyway, section 1.3, the applications version of this, we did the just kind of naked math, if you will, before. Now we're going to basically go word probleming. And here we go. Okay, I admit for this I stole a lot of problems out of the book, but here we are. So if you look in page 35, problem number 86, it basically gives you three equations. I'm going to get lazy and just go with two of them just to simplify the process here, but I'm sure you could put the third one on if you needed to. Basically what it says is graph them in a viewing window so that things look the way they should, meaning parallel looks parallel and perpendicular looks perpendicular. Now the problem, if you have a TI-83 or 84 here, is the standard window of standard zoom, if you will, of -10 to 10 and 10 to -10. It doesn't give you a true appearance what it should be, because mostly here's these two lines graphed on the TI-83, and you notice the slopes are opposite reciprocals, so they should look perpendicular to each other, but you can tell here this looks very obtuse right here, and then this guy looks pretty acute. So basically, if you just go into the zoom menu, go to the z-square option, and it changes it from the 10, 10, 10, 10 that it normally has to like something around -16 to +16 and maintains the 10 and 10. But what really is important is as you graph it here, you can look at these guys and they look a heck of a lot more perpendicular now. And so that's really what that question is asking you to do. Okay, now if we have an Inspire, it's a completely different story. I'm still on the same problem here, still the same two equations. The nice thing about the Inspire is its basic screen is actually set up in more of a square sort of format, meaning that if we have the 6.67 down to -6.67 and -10 to 10, like it shows on the regular screen, that's already squared up. So if you just graph the equations as they are with the regular viewing window, you do get a very nice perpendicular look to the thing. So basically it's one area where the TI Inspire works a little bit better than the TI-83. Okay, now I'm going to borrow from page 36, number 94A, and what it says there, of course, is the slope of a line representing revenue of $Y in terms of X days. What does the slope of M equals 400 mean in context? And hopefully this is obvious, but maybe it's not. Well, given the fact that my slope is 400, and of course, when I'm talking slope, I'm talking rise over run. Well, that's run, not vun, but I'm sure you understand. Alright, well anyway, moving right along. Okay, this 400 over 1, well, if we think of what rise, of course, is the y variable and run is the x variable, it's in y dollars, so the rise y dollars, that stands for dollars up there on the y variable, and then x is the number of days, so basically we have $400 per 1 days, so that's what that means. And again, the slope itself is always thought of as a rate, or at least usually thought of as a rate. So basically our revenue is simply, in kind of a more real-world context, $400 per day. So basically the thing is, once you know what the units are and which variable represents what unit, you can just make a rate ratio out of it, whatever you want to think of it as, and then from there it translates into some kind of a rate of change that you can then apply to real-world scenarios. Okay, now on page 37 we see problem 106, if we're looking at a book, and I know I'm sure most of you aren't. But anyway, in 1997 there were 4,076 J.C. Penney's, and in 2003 there was 1,078. And now we want a linear equation for the number of stores in terms of the year when we're using t equals 9 for 1999. And hopefully it makes a little bit of sense that we're going to kind of define our year in a special way to avoid having to plug in large numbers like 1999 or 2003 or whatever into an equation. By doing this, we can just give ourselves smaller numbers to work with, because quite honestly, we're going to have enough big ones in this problem, we don't need to worry about any other ones. And, well, since we have, well, T, but I don't know what my other letter is going to be, so I'm going to choose to use J for the number of stores. And then we've got T for the year since 1999. So, working with that, and then looking at the various information in the problem, if I've got 1999, well, that's t equals 9, so I've got kind of a point here where 9 is the year and then 4076 is the number of stores. Okay, in a very similar fashion, I can look at 2003 and say, well, hey, that's year, well, 4 more than 1999, so 4 more than 9, that's year 13 in the context of our problem. And then the number of stores is down to 1,078. And as soon as you've got 2 points, you can determine the equation of that line. So using our slope, which is what I want to do first, My good old y2 minus y1 trick. Not really a trick, of course, but you know what I mean. And 13 minus 9. And, okay, denominator works out to be 4. My numerator works out to be a relatively messy, negative 2,998. And though most of the time it's a good idea to use fractions, I think in the real-world context right here, decimals are a little bit nicer to work with. So that's negative 749.5. Again, thinking about what these variables represent, stores is like our numerator and years is our denominator. So the negative here means that we're losing almost 750 stores per year, and that's kind of a dramatic drop. But anyway, moving from there, now we're not going to use y minus y1 equals mx minus x1 because we've got different letters. Okay, we're looking at j versus t. And if you're kind of looking at what's going on, the t is like our x, and then the j, the number of stores, is our y. So realistically here, I'm going to do j minus one of the j's, or one of the y's, depending on what you want to say here. But I'm going to go with the 4076 for no better reason other than it's first. Okay, equals my slope is the negative 749, excuse me, 0.5. And then of course now it would be x minus x1, but again we're not using x, we're using t, so now it's going to be t minus, and then the time that goes with the 4076 is this 9. So I'm putting it right in there, closing it up. Okay, and from this point, I'm not going to bore you with the steps, but other than saying, okay, I would distribute the negative 749.5 and then add the 4076 to both sides. And what we would get there is a final answer for our equation of j equals our negative 749.5t and plus, brace yourself, 10,821.5. And that would be our equation in a slope-intercept form for the number of stores j based on the number of years since 1999 t. Okay, now problem 106 actually continues. I didn't put the rest of it on the screen yet because I quite honestly didn't have enough room to do both halves of it. But here's the original part that we just went through, and then here's the equation we just got as an answer. But what it wants you to do there is predict the number of stores for the 2008 and 2010, and ask, hey, are your answers reasonable? Well, so what we need to do is say, okay, well, for 2008, well, since 9 is number of years, or is 1999, for 2008, well, that's basically going to be t equals 18. Basically what I do is, if 9 is 1999, then I think of whatever the 0 is, and that'd be 1990, and how many years past 1990 is 2008? Well, that's 18 years past. In a similar fashion, 2010 is going to be t equals 20. Alright, so then the number of stores, that's what our equation's good for now. Nice easy thing to plug into to make some predictions. Granted, the numbers are a little messy, but the process is pretty straightforward. 749 times t, and I probably should have labeled this as, this will be the 2008 prediction. Alright, so I went 18 right there, and then we're going to go plus our 10,821.5. And typing that in a handy dandy calculator gives me a answer of negative 2669.5. Okay, and let's just not waste the time on it. If I plug in 20, I plug in a bigger number here, I'm going to have a bigger negative part, and it's going to give me an even bigger negative answer. So actually, let's just skip that for now and just come up with the are your answers reasonable kind of thing. Well, is it reasonable to have a negative number of stores? No. So basically, there's our predicted number of stores, which obviously makes no sense because let's all go out to the negative JCPenney. That doesn't make a whole lot of sense for us. So you have to kind of interpret mathematics reasonably. I mean, mathematics is great for some things, but then you do have to balance the real world off of it to make sure that what you're doing actually is sensical. Okay, now problem 108, if you're looking at the book again, which I know most of you aren't. A school purchases a printer, copier, scanner machine for $25,000, and after 10 years they're figuring it's going to have to be replaced, and it's probably only been worth about $2,000 at the time. So we want a linear equation involving the value v of the equipment during the 10 years it'll be in use. Okay, again, this is a situation where they gave us one variable and not the other, so we need to come up with our own for the second. So I think t is a pretty good one for time. So t is just going to be the number of years since we bought the copier, printer, scanner thingy. Alright, so again, kind of with the same thing as the JCPenney problem we just talked about. Alright, the t is going to be kind of our x, and the v is going to be kind of our y for this. kind of the whole independent-dependent variable thing, but if you need help with that, ask me in class. I'll be happy to explain it. But basically, for 25,000 bucks, that's when we just bought the thing. So basically, time is 0. Just things just out of the box. We're going to have something worth 25,000 bucks. And be careful as you're writing ordered pairs with large numbers with commas in them, so you don't get yourself confused about how things look. Okay, and then 10 years down the line, we know this thing's going to be worth only about 2,000 bucks. Okay, so again, there's our 2 points. And again, we can come up with a linear equation by just going with the slope and kind of following through on that. So our slope is 2,000 minus 25,000. And that's all over 10 minus 0. Alright, so we're looking at here a negative 23,000 divided by 10, which is negative 2,300. So we're losing 2,300 bucks in value per year. Okay, and then just going with the rest of this whole process. Although if you're tricky about this, 0, 25,000. Wait a minute, that is a y-intercept. So I don't really have to go through that whole process. And if you're paying attention, sometimes you can skip that depending on the points you're starting with. Well, heck, there's a b, y-intercept if you will, and there's my slope. So realistically, my value, which remember the value is our y variable for this case, is, well, mx, so 2300, and again, x is really going to be t in our situation right here. And then it's going to be plus b, so plus our b value in this case is going to be 25,000. So keep your eyes open, and sometimes you can save yourself a bunch of work. Of course, if we would have gone through all those steps with the point slope form, we'd eventually got this anyway, but why go through the work if you don't have to? And all this was asking for is our equation, so there's our final answer.